All right, well, thank you very much. I'd like to thank the organizers for putting together such a nice workshop. So much like we've been studying monopoles, cutting these dipoles in halves, I cut the title of my talk in half. So it's a search for new spin ices, and it'll be mostly a chemistry talk. So where to look for new spin ices and a bit of a cautionary tale of where not to look for spin ices. So Steve Rammel put up this rather depressing slide about Brits and their failed searches for poles. I want to mention that Canadians, on the other hand, have been looking for monopoles for a long time. Actually, we've been tracking a famous monopole in Canada for a long time. So that's magnetic North Pole. Not many deaths been reported to date. Although you could argue that we were British citizens back then, so the Brits point us in the right direction. But in all seriousness, it's a very vibrant condensed matter and frustrated magnet community in Canada. So there's lots of people working on this problem. I'm very happy to be working with lots of colleagues in Canada on frustrated systems. Okay, so throughout this talk, you're going to see this name Haidon Zhao. He's my former postdoc at the Magnet Lab. He's taken over a remnant group there. I was a faculty member there for a number of years before returning to Canada, but most of the work you're going to see has been started by him in some way. He's a fantastic crystal grower, and he's on the job market, I think, so if you see him, you should probably try and snatch him up. At the University of Manitoba, I have some graduate students here, so Harlan and Alana helped out with a lot of the recent measurements we've been doing, and then the usual cast of usual suspects that have been helping out with thinking about what's going on in these new spin ices and doing experiments, and of course various funding sources. Okay, so what I'm going to talk about today in this sort of framework for my talk is looking for new spin ices among different compounds. There are some very strict constraints you have in looking for spin ices, right? So I'm going to be showing what happens throughout this talk, what happens when you start to relax these constraints, where you have spin ice physics and where you don't. And of course there are other interesting things that pop up when you don't have spin ice physics, but when you're looking for spin ices, you want to find compounds that have isine-like spins. There's one-on-one anisotropy. You want weak ferromagnetic exchange, although you can have weak antiferromagnetic exchange as well, as long as you have a significant dipolar interaction that will overcome that, and you need strong dipolar interactions between the spins. So from a chemistry perspective, as has been pointed out by many people this week, the titanates have been studied the most, but if you look at the stability map for power chlorures, actually, there's only a narrow range of rare earths you can make among the titanates. But the reason why they're studied basically is because titanium oxide is very stable. You can grow large crystals in image furnaces. I'm going to talk about other compounds beyond the titanates, but the titanates will be sort of a model for understanding some of these new spin ices and new compounds. So where do we expect new spin ices to be found? So this stability field has been presented, I believe, by Michelle at one point. So this is looking at the A2B2O7 chemical structure, where you expect to see different types of phases forming. So this is under ambient pressure, and these are some high pressure phases here. So as I mentioned before, the titanates, you can only make certain power chlorures here among the titanates. So these ones, for example, the praseodymium titanate case doesn't exist. The praseodymium stannate exists, for example. Actually, a stannate would be a wonderful system to systematically look through many power chlorures, but there are problems with the stanates. There are chemistry problems with stanates, right? So you have stoichiometry problems with tin oxide at high temperatures, and you have to be really careful when you're trying to compare different or the same stannate compounds with each other. But I'm going to talk about where we want to look for new spin ices beyond the titanates. Notice there are these high pressure phases that I've emphasized here. We're going to talk about new high pressure phases, in particular the germanates, near the end of this talk. Okay, so as someone that does a lot of chemistry, I just want to emphasize that this is the lattice that theorists are interested in, but in the real world you have this titanium oxide lattice, for example, in the example of titanates, that's a support framework. When you're looking for new materials, you want to make sure that there's a match between the rare earth site and the B site, if you'd like, right? But we don't want that match to be too perfect, or else you'll have site disorder. So it's a bit of a chemistry game trying to figure out, trying to match different sites that are close in size scale, but really not too close together. But the power chloride lattice, even though I'm only emphasizing the power chlorures today, traditionally they were studied because they were, there's prediction that for nearest neighbor antiferromagnetic interactions on the for Heisenberg spins, you should have no long-range order. But it's actually a rich playground for varying these parameters, right? So looking at what happens when you have anisotropy, when you have exchange interactions, dipolar interactions, crystal fields. And all those would be important when you're trying to determine if you have a spin ice or not. Okay, so going back to periodic tables, so the chemistry person here, we're going to be looking at, along this series here, what happens when you start varying the B site and trying to combine different rare earths in this site. And we're looking at these three constraints. What happens when you start relaxing these three constraints? So we'll first look at the stanates with reference to titanates. So just as a quick review, there's only 2 known members here that are good examples of spin ice. It's not to say there's interesting physics in these other compounds. As you go across these series, I mentioned this week that terbium titanate is cooperative paramagnet. Gallium titanate has this unusual phase transition around 1 Kelvin. People are still trying to understand. And erbium titanate has this long-range magnetic state with the XY spins, but it's ordered by disorder mechanism. So there's still interesting physics to probe as you go across here, but the only known spin ices among titanates are dysprosium and holmium. Now, if you look into stanates, actually the properties are very similar, although there are some subtle differences. Right? So gallium stanate, I would believe to have long-range magnetic order. Erbium stanate as well, Steve Bramwell's reported that as long-range magnetic order, though we have recent work which suggests it might not. That might be a sample issue, right? The stanates are hard to deal with. You have to worry about stoichiometry. You have to worry about, it's really messy if you put these in the image furnace. You're not going to get good crystals when it comes out with the tin oxide just comes off your sample. But looking at powder samples, people have determined that dysprosium and holmium are spin ices, and this terbium stanate is not a cooperative paramagnet, but people believe that actually has a partially magnetic ordered state. So in the stanates, these are the only 2 known spin ices throughout that whole series. Okay, so I'm using this diagram as sort of a conceptual framework for this talk when we're trying to characterize spin ices. This is a famous Den Hertog-Gingras phase diagram, which was made in the days before monopoles took over everything. So this is looking at just this deceptively simple Heisenberg or Eisen-like Hamiltonian, where you have an exchange term and you have a dipolar term in here for these Eisen-like spins. And this is the phase diagram that you get. So there's a spin ice on this side, antiferromagnet on this side, and there's a phase transition near roughly J over D is -1. So you notice that there are actually some parts of that phase diagram where you can have antiferromagnetic J, but you still have spin ice physics, and that's because you still have a dipolar interaction, which will stabilize that state. So we're looking for new spin ices. I'm going to try and reference them with respect to this phase diagram to figure out where we're at and see how applicable this phase diagram is. I'd like to mention that when you're looking at monopole species, they tend to be in this region here, right? So as you approach this phase boundary, you have a higher density of monopoles. And one of the goals of our research is actually to look at what happens as you approach this phase boundary. And I'll discuss this when I discuss the germanates at the end of this talk. Okay, so I'm just mentioning this as a cautionary tale, right? So if you have other terms in the Hamiltonian, like crystal field effects, you basically can't use this phase diagram anymore. So for example, if you look at terbium titanate, terbium stanate, you can look at J over D, you get roughly -0.5, so you might think, oh, if I make this compound, it's going to be a spin ice. It's not, right? It's not because we're only including this exchange term and this dipolar term in the Hamiltonian. As Michel Gingras pointed out, you can think about different axes that can come on here for different other effects, such as crystal fields. And crystal fields are extremely important towards understanding the terbium titanate and terbium stanate, right? And very subtle crystal field effects at low temperatures can influence the ground state. Terbium titanate is a cooperative paramagnet down to 50 millikelvin. Terbium stanate has this partially ordered state. People are still trying to understand. It could be due to relaxing of the Ising constraint. There's some discussion of that this week. So if you have a low-lying crystal field state, should be another constraint actually looking for spin ices. Even though it might lie in this diagram here, you're actually in a sort of no man's land, as Michel pointed out in this way. There's never a parameter that you have to vary here. So you can't use this as a predictor for looking for spin ice states if you have other perturbations. They matter. Okay, what about spin ices without Ising spins, right? How strict is that constraint? This is looking at data on ytterbium stanate. We heard a lot of information this week in talks, nice talks on ytterbium titanate. Ytterbium stanate, again, has very similar susceptibility to ytterbium titanate, so it has no long-range order down to 0.35 Kelvin. The Curie-Weiss constant slightly higher, so a little more ferromagnetic at 0.43. And if you measure the heat capacity sort of naively, and you compare that to non-magnetic lanthanum stanate, integrate that up, you get something close to spin ice, right? So you may think, oh, wow, I discovered a new spin ice. You haven't, right? So you have to worry about what happens down here, right? Because ytterbium titanate orders at 0.24 Kelvin. We've only measured this down to 0.35, right? So you have to, of course, look at, I'm not the only Canadian that can have cheesy flame effects. So, so if you look at ytterbium titanate, right? So ytterbium titanate has a very similar shape at low temperatures, right? But we've only measured down to here if you look at that scale here. So there could be an ordering transition here. So you can be fooled by entropy. It's not a very good argument for looking for spin ices. You really need to combine various probes to look for this, right? So actually I expect there'll be a peak down here, and it'll have properties similar to ytterbium titanate. We'll look at this in more detail at low temperatures. Okay, what about small moments, right? So I mentioned that large moments is one of these strong dipole interactions for spin ices. We were looking at praseodymium stanate. I mentioned that titanate doesn't exist. It's because of a size issue. The praseodymium and titanium size doesn't give you the cubic particle lattice if you compare the A/B ratio. However, you can make the stannate compound, and in principle, you can use the Hikaru phase diagram to look at compounds that have small moments, but because your D is so small compared to things like holmium dysprosium that have 10 Bohr magnetons compared to a few Bohr magnetons, you're going to be either far to the right or the far to the left of that phase diagram. But this is some data from praseodymium stannate that we prepared. It has a characteristic anomaly at low temperatures, and you recover some of the entropy when you apply a field. If you measure Curie-Weiss susceptibility, it has a weakly ferromagnetic Curie-Weiss temperature, and there's no ordering reported down to 0.35 Kelvin. This is looking at the heat capacity of the stannate compared to holmium titanate. And if you look at the holmium titanate, you get the spin ice entropy integrated back. The praseodymium stannate has roughly 75%, so there's some missing entropy at low temperatures. And again, if you apply a field, they look similar in a field. They recover basically the same entropy among the two different compounds. So what's happening? Is it a spin ice or is it not? Well, you have to look at some other probes, look at this with neutron scattering. So we first showed there was no ordering down to 200 millikelvin of neutron scattering. And we did some inelastic spectroscopy, so we found there was well-separated crystal fields, an order of around 200 Kelvin or so. Looked at the elastic scattering, we saw that there was this characteristic sort of a spin ice-like profile. This red fit is to just a spin ice model that we use, and there's some missing intensity at low Q that I'll mention on the next slide. So it's not the best model, but it looks like in elastic time scale anyways, looks like we have these this 2-in, 2-out configuration on each tetrahedra. The surprising thing for us was looking at the inelastic spectrum, where we noticed that there was a lot of spin fluctuations at low temperatures, right? So this is very different from spin ices, which are basically static on the sort of time scale of this time of flight measurement. So the idea we had was that locally you had this 2-in, 2-out configuration in each tetrahedra, but you had some sort of spin fluctuations at low temperatures, which could possibly be some sort of tunneling between different states. So we called this the dynamic spin ice when we published this paper. And we did some in the same paper, we did some high-resolution neutron scattering measurements. If I can direct attention to this middle plot here, the green data here is holmium titanate. So you can see it's really static on this time scale. The praseodymium stannate has this unusual low-energy spin fluctuation, and we extracted a characteristic time for that so we can compare it to its AC susceptibility measurements. And if you look at the gap for this, it gives you roughly 1.4 Kelvin. So that reminds us sort of the gap that's seen in dysprosium titanate. So dysprosium titanate, if you look at this AC susceptibility data, you can call this the monopole region now if you like, but at high temperatures it has this thermally activated region looking at crystal field excitations. Then it has this sort of flat region where it has anomalously low activation energy barrier, so that's interpreted as quantum tunneling between different states before it is a monopoles. And then you had this anomalous rise at lower temperatures. So our original idea was that we had some sort of a quantum tunneling between these 2-in, 2-out states. So Inoue-san, after we published our results, Inoue-san started discussing what really happens in praseodymium stannate. So we're happy to see this paper appear. There are some issues still in praseodymium stannate. The low temperature crystal field states it's a non-Kramer's magnetic doublet. We've been criticized that perhaps we have excitations between low-lying crystal fields, and that's what we're seeing in our spin excitations. But they did some recent theory work on this, and they showed that it's an effective spin 1/2 system, and they did some complicated calculations to show how the exchange works in this compound. And they actually modeled our inelastic data, and they actually got a better fit than us from looking at their interpretation. So in their interpretation, we have the quadrupolar component is important towards this order. So we have ice-like properties among ferroquadrupoles at low temperature. So it's a cooperative ferroquadrupolar state, if you'd like. So they called this paper quantum melting of spin ice. So praseodymium stannate isn't a traditional spin ice, but it may still have interesting properties that are still waiting to be explored. Okay, so I want to jump towards the germanates. So I've talked about samples you make at ambient pressure. The germanates you can't make at ambient pressure. You might think naively in looking at the periodic table, germanium's above 10, so I can make germanium 4+ power chlorus. It's too small, the lattice collapses. You get these well-known pyrogermanate phases that Pierre Schiffer and others have looked at, but they're not pyrochlor phases. But under high pressure, under 6 gigapascals of pressure, you can make samples, very, very small samples, in order of around 20 milligrams or so per reaction, but you can actually stabilize these phases in the cubic pyrochlor forms. So I'm going to talk about these compounds. We believe terbium germanate is a cooperative paramagnet, and these two are new spin ice compounds. So here's so for the chemists out there, here's the Rickwell refinements that we've done in this. So the A constant for pyrochlor is usually around 10 angstroms. You'll see in this case it's significantly less than 10 angstroms you might expect from the small size germanium. And we get a good fit, this characteristic 111 peak that appears at low angle, which is our signature pyrochlore phase. The interest in actually looking at these, I mentioned before, is that we're looking for new ways you can look at monopoles. And with a much smaller lattice, actually, you have a smaller chemical potential for making monopoles. So you may imagine on these compounds you have a higher density of monopoles, and that's what we find experimentally. So if you really want to look for monopoles, it's actually in these compounds compared to the sort of canonical titanate compounds. So because there's some interest in terbium titanate, I thought I'd just mention some data on terbium germanate. It has properties very similar to terbium titanate. So you look at the Curie Weiss susceptibility, get a Curie Weiss temperature around roughly minus 21 compared to minus 19 in terbium titanate. And of course, there are crystal field effects that we have in here, but you can sort of naively understand this as the lattice is smaller, so there's a larger J, so there are stronger spin-spin interactions. And if you look at the heat capacity at low temperatures as compared to a PRB paper, it does look very similar. So it looks like, so you expect that the low temperature magnetic properties are probably similar to the germanium titanate, although we don't have enough sample to do neutron scattering. We only have on the order of milligrams of this so far. But everything is shifted, right? So the crystal fields are shifted due to the different exchange that you have in this compound. So small lattice, larger J, stronger exchange, and the crystal field, this one shifted down a bit, and this one shifted upwards a bit with respect to terbium titanate. But when we start just measuring these compounds, we're trying to get enough neutron scattering, but it's going to take a postdoc a while. He's going to tear his hair out. Okay, so on to the other germanium pyrochlores that are new spin ice candidates. This is looking at the entropy. So Jason Gardner insisted that we plot this because everyone's been plotting this wrong for almost a decade now. So now we have the residual entropy here of R log 3 halves, and it goes up to 2R log 2 for looking at these samples. So the blue squares is the entropy you get from dysprosium germanate, and the red squares are holmium germanate. So we recently published the results on dysprosium germanate Nature Communications. That's where these figures are from. Now, before we go on to dysprosium, I mentioned some of the properties of the holmium germanate. We have a paper that we're preparing for Freitas of Letters. This is just showing you that across the series, if you go from tin to titanium to germanium, you can have a systematic change of your lattice constant. So you go to higher 2 theta, which means going to lower and lower A. The Curie Weiss constant is roughly 0.06, right? So slightly ferromagnetic, but there's also a dipolar contribution to that. And we've done AC susceptibility measurements down to low temperatures in this compound. It actually looks very similar to dysprosium titanate. So it has this. So it has these two features as a peak around 1 Kelvin or so, and then their peak around 15. And if you track their temperature dependencies, you can extract 2 energy scales. So one of these is the crystal field regime 196. And your own is a so-called glassy regime around 20 that they found for dysprosium titanate as well. And because holmium has this nice isotope compared to dysprosium, we actually made around 0.3 grams of this. It took Haidon about 6 months to make this sample, but we got enough to do a D7 experiment to see if it really is a spin ice or not. This is looking at the magnetic scattering that hasn't been scaled properly, but I'm just showing you dysprosium germanate holmium germanate compared to dysprosium titanate. And you can see that it has a characteristic sort of spin ice-like neutron scattering profile. So we're doing these reverse Monte Carlo calculations right now to work out the details of that structure, but naively it looks like that's a new spin ice. So I'm going to shift my attention to dysprosium germanate, and one of the reasons why is shown nicely in this figure that we published in this paper recently. This is looking at some sort of reduced temperature scale versus monopole density, right? And we just reduced temperature scale by a characteristic monopole energy. And you'll notice that if you're at any fixed temperature here, dysprosium germanate will have the highest concentration, if you'd like, of monopoles. Actually, it's an order of magnitude different from dysprosium titanate, right? So if you're really looking for monopoles, you want to look from a system like dysprosium germanate, just stick out like a sore thumb. So that's why we concentrate on this compound and did a rigorous analysis of the specific heat to learn something about what's going on with the monopoles. So actually, muons aside, one of the first bits of evidence for monopole physics was looking at the heat capacities. This is a fit done dysprosium titanate, so the blue is this monopole fit that they did. So what we did is we took basically the bi-Huckel theory and used it with dysprosium titanate to see how good of a fit it would be, right? And what we found was that, I know Claudia gave us a nice talk showing that pairing is not very important for these BRM pairs of monopoles at low temperatures, but it actually is extremely important for dysprosium germanate, as I'll show in the next few slides. So here's the heat capacity of germanium pyrochlorus. So we're comparing this in this plot here, the dysprosium germanate versus dysprosium titanate. And this is actually predicted by Den Hertog and Gingras that when it shifts to lower temperatures because of lower chemical potential, you get a sharpness of this function here, and eventually it should reach this first order transition where you go to an antiferromagnet, right? But this is just comparing these two and see what they look like. And when we fit this is a fit that we done to the Bi-Huckel theory with the chemical potential. So chemical potential is smaller than you have for dysprosium titanate, which is the reason why you have much more monopoles at low temperatures. So what we decided to do was look at the heat capacity at lower temperatures, because you should have, as the monopole density becomes really high, you should have significant corrections to for Bjerrum pairing at low temperatures. So this is showing you the internal energy we extracted from the heat capacity. So in the inset here, first of all, we have dysprosium titanate compared to dysprosium germanate. The solid line here is the fit to with Bjerrum theory plus the Bi-Huckel. The dotted line is just the Bi-Huckel. So as Claudio mentioned, Bjerrum pairing does not make a difference at all for dysprosium titanate. Right? There's only a very, very small difference between these two. However, for dysprosium germanate, it's essential. You get essentially the Ron fit if you do this. And there are really no adjustable parameters within this theory. You're using parameters you've already defined. Right? So you have to use the Bi-Huckel plus this Bjerrum theory in order to fit this data properly at low temperatures. Right? And it's not even really a fit. You're just taking the parameters that we extracted before. So if you're really looking for monopoles, there's a high density here, and this sort of pairing effect is noticeable and measurable in these at low temperatures. So we can now put these on the Den Hertog-Gingras phase diagram, and so this is looking at, so I plotted this on log scales, need some details a little more, a little better. So these are the known spin ices except for dysprosium germanate, right? So dysprosium germanate has different J constants, lower chemical potential, and you're really approaching this phase transition with dysprosium germanate to this no man's land. I'm trying to figure out what's there. Now, it should be like a first order phase transition here, but we don't know what happens in this region. Perhaps you can tune a some error parameter like pressure. Perhaps you can have one of these Higgs phases that Paulo was talking about, for example. We don't know. But I'm excited about this work because now we have these samples. We can think about applying pressure and doing various things to approach that phase transition and study what happens when you have evolution from a spin ice and antiferromagnet, or from a monopole to an ordered monopole like NT, if you'd like. So just to start winding up, so I think the most promising avenues towards exploring the spin ices are these germanium power chlores, although there are some other surprises on the way, such as these praseodymium steinate compounds, the so-called quadrupolar ice state. But the Den Hertog-Gingras diagram still works beautifully for describing all these compounds. Now, where do I think that the chemistry is going in the future for these? Well, there's other candidates you can think of beyond the germanates. And there are lots of groups working on different types of compounds, including us. So you may think about the zirconates and the hafnates, for example. You can make both these samples in power chlor form. However, you have to worry about site disorder, right? So the B site and A site are going to be roughly the same size. So you have to make sure you have very good samples. But there's some Japanese groups, around Matsuhiro et al., for example, that have shown you can grow very large single crystals of these compounds. From a chemistry perspective, the crystal growth is challenging because zirconium oxide doesn't melt till extremely high temperatures. So you have to get in the order of 2500 C and higher. And at those temperatures, you're losing your rare earth oxide as well. So you have to add extra praseodymium oxide in this case in order to get the right stoichiometry to counterbalance what you're losing, right? But there's some preliminary evidence on this that suggests that there could be interesting sort of spin ice-like states in these compounds here. But again, this is sort of in the very early days. So the zirconates show some promise. They're not very stable going across the whole rare earth series. You make it for praseodymium, neodymium, but it starts to get tougher as you go across, and there's an lanthanide contraction that's working against you. You can also look at the hafnate compounds, and there's some preliminary work being done on hafnates, and that's a different problem. It's a financial problem. Hafnium oxide is more expensive than zirconium oxide, but in principle, you should be able to make these compounds as well. But I just want to stress that site disorder is an issue, right? So you have to really be sure you've done the chemistry right and the annealing right to make sure that you have the right compounds. So I think I'm keeping you from lunch, so I'll just leave that there, and thank you for your attention.
So for the praseodymium compound, I think in terms of synthesis, right, praseodymium is really prone to have tetravalent valence, right? And so across oxides. So is there any problem here in these compounds?
Well, you have to worry about that. And there's different types of praseodymium oxides you can start with in the beginning. So there's praseodymium 6011, for example, and other types of oxides you can use. Some of them work and some of them don't in the synthesis. So you're right. If you avoid that tetravalent, your reaction will be much cleaner.
Okay, so I really look forward to your new results in the future. But that is like that one case. But I have a question on yttrium stannate. And we all know nowadays know that yttrium titanate has really have some kind of problem in sample dependence. But now we know that in the best sample, best qualified sample a single crystal sample shows a ferromagnetism in the low temperature. And so we are looking for, it's really nice looking for a quantum transition point between, Coulomb liquid phase and Higgs phase. And that is a quantum Higgs phase transition. So is it possible, could you comment on the possibility to observe such a kind of fantastic phenomenon in this compound? Including some possibility of sample dependence?
Well, only powder examples exist, right? So it'd have to be, if you're applying a field or trying to get to some air phase, right? You're applying it to a powder, right? So it's just it'd be difficult to see in this type of compound. If you're looking for these new phases, ytterbium titanate's the way to go, because you can make crystals, you can apply fields wherever you like. But applying fields to a powder, you can never be sure what you're doing, right? Because you're random orientation of crystals.
Just got a quick question. So this very nice result in the germanates. You have a different monopole chemical potential compared to the Coulomb interaction. So another way you can change the monopole chemical potential, albeit in a different way because it's a staggered one, is by applying a field in the 1-1-1 direction. And there, of course, even though it's staggered, the nice thing is it's actually continuously tunable. Do you think the spurium corrections and all that could be measured in a sort of more systematic way by measuring things like magnetic specific heat at low temperatures? Or specific heat in a magnetic field at low temperatures.
Right. That would be a really great experiment if we had single crystals, but we don't have them. It's you get really small powder samples. I suppose you can think about a way of aligning the powder somehow magnetically, and then think about how you can do these types of measurements. But until single crystals exist, it's hard to see that.
Can you make solid solutions of germanium and titanium using this high pressure route?
That's a great question. I believe you can. You have to worry about other phases like there's a perovskite phase and some other phases that come up, but I believe you can, yeah.
In the praseodymium tin compound, is the praseodymium magnetic? Are you sure of that?
We're not sure. So it's rated to be a non-magnetic Kramer's doublet, so I'm not really sure. Because we're happy that the quadrupole component appears, so,
yeah.
but we're not really sure. We see a signal of neutron scattering, just use a dipolar probe, but it's really hard to say how magnetic it is.
I don't know whether you saw Plato in USR and you showed it, but in that case there could be some hyperfine enhanced nuclear magnetism.
And you have to
that
worry
could
about that
contribute to
prastinium.
this plateau.
Yeah, I did mention that there is a Schottky anomaly you have to subtract from the prastinium, but right, there's a nuclear component you have to worry about.
Maybe I have a comment on the last questions on possible nature of the prastinium moment. So actually, there are several other experiments, and show that anisotropy of the magnetization curve, which is quite reasonably understood from the usual 1-1-1 anisotropic Ising moment with some kind of quantum fluctuations. And actually it shows the metamagnetic transition along the field, and the field along the 1-1-1 directions. So I think it's pretty consistent with that picture.
I have a small question. If I understood correctly, that you mentioned that the Weiss constant of your germanate compounds, holmium germanate is weakly ferromagnetic, 60 mK. But in your dysprosium compound, it's very largely antiferromagnetic.
You're moving towards, as you get the small and smaller lattice, it actually becomes more antiferromagnetic, the exchange between the spins. But there's a dipolar component on top of that,
but
right?
Both compounds shows very similar heat capacity data, showing a 1K peak.
But they're different places, right? So dysprosium compared to holmium?
Yeah, germanates compounds.
The germanates, yeah. So here are the... they're at different... This is the integrated specific heat, but they're at different temperatures, right? Because they're shifted.
But small shift?
This is like a Kelvin shift, right? At least Kelvin and a half.
Okay. Any questions or comments? Okay, just we are on time. So we move to our photograph. Okay? Thank you very much.